Hi, we are Marina Llano, Jaime Starellas, and me, Laura Pedrotet, and we're going to present you our project about quantum machine learning. We will start by briefly discuss conventional machine learning. Machine learning is a branch of artificial intelligence that it was defined in the 1950s by Arthur Samuel, a pioneer in AI, as the field of study that gives computer the ability to learn without explicitly being programmed. The key idea is that machine learning allows computers to improve performance as they gain more data. So how does it work? First, we start with data which is collected and prepared for training. Then the model is trained on this data to find patterns and relationships. And over time, programmers can adjust the model to improve its accuracy. The results can be descriptions, prescriptions, or predictions. Machine learning models are divided into three main types. The first of all is supervised learning, that the model is trained using labeled data where inputs have known outputs. For example, in this slide, we have a model that classifies pictures of cats and dogs. During training, each picture is labeled as cat or dog, and once it's trained, it predicts labels for new unseen pictures. Then we have unsupervised learning that the model now works with unlabeled data, finding hidden patterns or clusters. Now imagine we give the model a set of circles in various colors, as we can see, red, blue, and green, with no labels. Then the model will group them by similarity, in this case, colors. Finally, we have reinforcement learning, which is like learning through trial and error. The program is called an agent, and it learns by interacting with an environment and receiving feedback. For example, here we have a robot that learns to recognize shapes by trial and error. Correct actions will earn rewards, while mistakes get penalties. So we're going to go now through the basics of quantum computing. Let's compare quantum computing versus classical computing to understand why we need quantum. So classical computers are great for many tasks, but they hit limitations when faced with optimization problems and high-dimensional data. These tasks require enormous computational time and resources. While quantum computing addresses these limits, thanks, among others, to these quantum properties we are all familiar with, that are superposition, entanglement, and also quantum gates. Now we can go to quantum machine learning. So building on the quantum properties we have just discussed, researchers are exploring how quantum computing can enhance machine learning. Even though current quantum computers are still in their early stages, they are already showing potential properties to outperform classical methods in specific tasks. Quantum machine learning leverages the unique strength of quantum computing to tackle challenges in data analysis more efficiently than and even solve problems that classical approaches struggle with. So the goal of quantum machine learning is to combine the best of both worlds: quantum power for speed and complexity, and classical machine learning methods for adaptability and practicality.
So there are four strategies on how to combine machine learning and quantum computing based on if one considers the data was created by a classical or a quantum system, and whether if the computer that processes this data is classical or a quantum device. Classical data using classical computers would correspond to the traditional technique of machine learning that Laura has explained, using algorithms that are inspired by quantum computing to improve classical methods. This would be a quantum-inspired or enhanced machine learning. But in this review, we will center on the CQ scenario, which is classical data using quantum machine learning algorithms. This approach leverages quantum computing to analyze traditional datasets, such as image or text, generated by classical computers. In this setup, the data is processed by quantum devices to extract valuable insights. We have two approaches in the CQ scenario. The first one involves adapting a classical machine learning algorithm to work on quantum computers to achieve speedups. Classical data has to be encoded into quantum data, this process is called quantum encoding, before being processed by quantum devices. So this quantum device processes quantum data, and this produces quantum outputs, and this has to be converted back into classical data for interpretation. The second approach focuses on designing quantum machine learning algorithms based on quantum subroutines, which are totally different from classical algorithms, such as Grover algorithm, which we have seen in class, quantum phase estimation, variational quantum circuits, etc. Today, quantum machine learning algorithms can be grouped into two main strategies: fully quantum machine learning, which would be quantum algorithms designed to run on quantum computers, and then there would be the hybrid algorithms, which combine classical and quantum algorithms to enhance performance and reduce learning costs. We will focus on this approach because it is the most developed nowadays. These hybrid algorithms can be subclassified into four categories. First, we would have the parameterized quantum circuits, which are quantum algorithms that rely on adjustable parameters. They can be used in two main ways: to encode data or as quantum models, where the parameters are optimized during the training. Then we have also the quantum optimization problems, which solve optimization challenges by applying quantum methods to classification and regression tasks. Thanks to the intrinsic parallelism of quantum computing, both of these kinds of algorithms have been demonstrated to work more efficiently than the classical counterparts. The following two categories are quantum neural networks, which I will explain now, and quantum kernels, which Jaime will explain the application we did focused on quantum clustering. Quantum neural networks are essentially feed-forward neural networks composed of quantum neurons trained using quantum unsupervised learning. In these networks, classical inputs are encoded into quantum states and processed through these quantum neurons. These neurons use quantum gates like rotation and CNOT gates to compute the outputs. One example of this kind of algorithms would be the quantum CNN, which is a convolutional neural network. These networks have the ability to extract features hierarchically throughout layers, with the convolutional being the most important. To adapt CNNs for quantum computing, one option is to use a convolutional layer or a quantum convolution. These layers replace classical convolutional filters with quantum circuits, creating a convolutional neural network, or a QNN. These convolutional filters process local sections of input data by encoding them through quantum circuits, similar to how classical filters operate, but leveraging quantum mechanics. This is an example of a QNN designed by Bew and his colleagues in 2024. And these researchers compared a CNN, a classical, and a QNN, and the quantum approach showed a clear advantage. Next, there would be the quantum kernels, which, as I have said previously, Jaime will introduce now.
So having explained this, we thought that it would be a great idea to do a quantum machine learning algorithm ourselves, and that's what we worked on. We worked on Qiskit. What we did is something called a K-clustering algorithm, which is a kind of a unsupervised machine learning. What it basically does, so the objective of this algorithm is to cluster data points that are similar, right? So if we have a random data set, as we can see on screen, we generate two centroids randomly on your data set, and you calculate the Euclidean distance between these points, and then you update this distance iteratively in a way that minimizes the distances between the centroid and the points around it until you reach an equilibrium. Of course, calculating the Euclidean distance in 2D, it's not something difficult, but as the dimension increases, the complexity, the power needed becomes much higher. So here's where quantum computing comes along, right? So we have these 3 columns, 1,000 rows data set, and instead of treating them as each a single independent data point, we turn each row into a quantum state, and we use the quantum properties as fidelity is to calculate the distance between the states, thus reducing the dimensions of the problem. The distance now will be 1 minus the fidelity, and now we just essentially calculate the fidelity between all the different data points. And here we can see the results of our algorithm, right? On the left, we can see the initial distribution of our data points, which we just initialized as random data points. We can see the center, the centroids that we spoke about, which are just randomly chosen, in this case, just right in the center. And then just by iterating them, we can reach to the final distribution, which is on the right. And we can analyze these results as, because it's a random distribution, the distance between all the points are pretty much going to be the same. So if the centroids are probably going to be in the center and reaching this nice pattern, right? And so finally, to conclude with the project, we've spoken a lot about what quantum machine learning is and the current state of the art. Of course, quantum machine learning is still not something that you can work purely. So you're actually working with classical computing and quantum computing at the same time. And this is, of course, due to the low efficiency, low accuracy of the quantum computing at the moment, due to noise, due to performance issues, etc., etc. And this is, of course, due to the lack of investment at the moment. In future steps, more research and more investment should be pursued. So thank you so much. I hope you enjoy the presentation.